Hi, and welcome back. Um, this is the second video for Lecture 2, which is Chapter 1 in University Physics 2. And in this lecture, what I'd like to do is to talk more about the relationship between temperature and heat. Now, we know from our discussion last time that we think of temperature really as the motions of the atoms and molecules that make something up. So that said, what I'm going to be showing you today are macroscopic relationships between heat and temperature. And I don't want you to get these things confused with what's really going on, say, behind the scenes at the microscopic level. So let's not forget that temperature really is just the motions, or it's related to. It's actually sort of like the average kinetic energy of the motions of the atoms and molecules that make something up. So remember, temperature really is kinetic energy. Now, so I can give you examples of this. One of which is something that I'm sure most of you are familiar with. If you think of an oven, so let's pretend that this is an oven, and maybe, so this is side view, and maybe this is the door right here. We'll put a handle on it. So there's a handle to your door, to your oven rather, your oven door. And so if you think of what's going on inside your oven when it's off, this is the inside has the same temperature as the outside. If you were to open the door, you would not get blasted in the face by air, right? On the other hand, if you turn the burner on the inside and you let it heat up, maybe you put it on 375, 400 degrees Fahrenheit, what you'll notice is that when you open the door, you get blasted in the face by hot air. And the reason is because the atoms and molecules of air on the inside of the oven are constrained to stay on the inside by four walls, a roof, and a floor. So when you heat these things up and you make them move around faster, okay, when you open the door to this, what you're doing is removing one wall of the container that's keeping them on the inside. Now, when it wasn't heated, the temperature on the inside and the temperature on the outside were the same. So the motions here of the atoms and molecules were the same as the motions here of the atoms and molecules. So what that means is there was no real bulk flow of material from the oven outwards or from the outside to the inside. And even if there was, you wouldn't really notice it because the atoms and molecules are all moving at the same speed. Now, when you heat up the air on the inside, since they're moving faster, when you open the door, there is a bulk flow outwards because the air molecules and atoms on the inside are moving faster than the ones on the outside. So you remove a wall to the container, they go flying out. New air comes in to fill it because it doesn't create a vacuum or anything like that on the inside. And so again, this shows you that in this case, the temperature that's the inside of the oven has is what's powering the motion of the particles, and as a consequence is the reason why you get blasted in the face by the air to begin with. Likewise, if you think of cooking something on the stove in a pot, let's pretend that you have a pot. Here's a handle. You got water in it, so here's some water. So you've got water molecules on the inside of the pot. Now, before you add heat to the pot and to the water on the inside, the water molecules themselves really aren't doing anything interesting. Now, when you add heat in, what happens is they move faster and faster and faster. Now, if you were to put seasoning in the water, like pepper and stuff like that, and let it sit at the top, then what you would notice is the temperature of the water on the inside of the pot goes up. If you were to look down on the top of the pot like this, so like here's the top view, if you will, what you would see would be these little bits of seasoning begin to move around faster and faster and faster on the surface. They may even dip below. Okay? And now the reason why they're moving is because they're bounded on all sides by water molecules. And as these things move around, they sort of drag the little bits of seasoning around with them. And as the temperature goes up, they experience more motion. And as they experience more motion, you see the particles themselves move around more. So again, this is sort of direct observational evidence, in the realm in which we live, in the macroscopic world. So this is evidence in the macroscopic world that temperature really is just, like I said, the average kinetic energy of the atoms and molecules that make something up. Now that said, just for reference, in the past when we've dealt with concepts like energy, we've used E for the total amount of energy. We've used things like K for kinetic energy, and we use things like U for potential energy. Now, in the study of thermodynamics, we use the letter Q to denote heat. Now, there are two different units that you see used for heat. The most common one, the one that we use in the sciences, is the joule. It's the same joule that you see when we talk about energy. There is another unit of heat that's called the calorie. Now, the calorie is a leftover. Before we had a rough idea as to what temperature really was, there was this thing that was called phlogiston theory, and I'm not going to go into any real detail about it, except to say that the unit of heat was the calorie. Now, there's a relationship between calories and between joules. 1.000 calories is equal to 4,186 joules. Now, so there is a such thing as something called a food calorie. When you look at the side of a box of ramen noodles or something like that, and you look to see how many calories it is, you're looking at food calories. Those calories are not the same thing as these calories, although there is a relationship between the two. One food calorie is the same thing as 1,000 regular calories. Okay? If you've ever been to the gym and, you've, say, run on the treadmill like a hamster or something like that, you may have seen on some treadmills when they do their little calorie counting, they might have kcal there. And that's the reason why. Now, so, that said, what I'd like to do is to look at the macroscopic relationship between heat and changes in temperature, and also what happens to the heat that does not cause a change in temperature. Now, we're going to get to that here in a moment. But before we do, what I want to do is to think about situations in which the applied heat that we have put in, if you will, causes a direct change in temperature. Now, so that said, let's see here. If you think of, say, cooking something on the stove, we know that when you turn your burner on your stove, what's happening is heat is going into your, say your pot and also the water that's on the inside. Now, as a consequence, you experience a change in temperature, or at least the pot does and the water on the inside. Now, if you were to conduct some experiments looking at the amount of heat added and the corresponding change in temperature, what you would see is that for most situations, the relationship is a proportionality. It's a linear relationship between the two. Now, so if you've ever cooked something on the stove again, like for example water, you know that the amount of heat that you have to apply to get your water to change temperature depends also upon how much water you have. In fact, again, were you to do an experiment, you would discover that there is a linear relationship between how much heat you need to apply and the amount of matter that's there, the mass. Now, this is really it. When you try to heat something up, the amount of heat that you need to apply depends upon how much stuff you have and also the change in temperature that you're looking for. Now, as a consequence, we can write that when you add heat in, the corresponding change in temperature depends upon the mass and the amount of heat. So we're going to do what we normally do and put an equal sign here. Our constant of proportionality we're going to call lowercase c. M is delta T. This C right here is called a specific heat. Now, so if you look at the units and you think of Q as being measured in joules, C is going to have units of joules per kilogram degree Celsius or Kelvin. It ends up being the same either way. And that's because Celsius and Kelvin use the same standard. Now, so the way to think about this is that if you were to add heat into something, whatever the specific heat of that something is, that material it is that you're trying to heat up, we'll say just 500 joules per kilogram degree Celsius. What this means is that for every 500 joules of energy for that material that you add into it, you will cause 1 kilogram of it to increase its temperature by 1 degree Celsius. Now, this is also a reversible process. You can take energy out. Okay? So if you took heat out, this would be how much heat that you needed to take out to take 1 kilogram of that material and drop its temperature by 1 degree Celsius. So the specific heat tells us how well a material gives up or receives energy. Okay? So Q is equal to C times M times delta T. Now there's another version of this, which I'll write down later on, that depends upon something called heat capacity, and that is related through number of moles as opposed to mass. But in the physics world, we like to deal with mass as opposed to number of moles. It's just a quirk, if you will. Now, some examples of specific heats, and I'll use water and its 3 states of matter just as a starting point. You have solid water, which we call ice. You have liquid water, which we typically just call water, and then you have gaseous water, which is steam. So for water, solid water has a specific heat of about 2,090 joules per kilogram degrees Celsius. So what that means is that if I want to raise a block of ice's temperature up by 1 degree Celsius, 1 kilogram of it, I need to add this much energy. Okay? Now, compare this with liquid water. 4,186 joules per kilogram degrees Celsius. Steam, or gaseous water, is somewhere around 1,520 joules per kilogram degrees Celsius. Now, different states of matter, different specific heats, and that's because how close the atoms and molecules are to each other and how strong the bonds are, if the bonds are even present, well, all those factors are going to contribute to how well that thing receives energy or how well it gives it up. Now, so that said, let's work an example. How much heat is needed to raise 1 kilogram of water from 1 degree Celsius to 99 degrees Celsius? Now, so in these series of problems that I'm going to work, what I'd like to point out is that the process has changed a little bit, because now when you add in the fact that material can sit in different states of matter, you need to take into account the fact that if you're dealing with a range of temperatures, it's possible that you may encounter a phase transition. For example, your material might turn from a solid to a liquid, or a liquid to a solid, a liquid to a gas, or a gas to a liquid, or even from a solid to a gas, or a gas to a solid. Okay? So thankfully, I know I'm dealing with water here, and I know that the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Between these two temperatures, I'm dealing with the liquid state. And as a consequence, I know that I have a specific heat of 4,186 joules per kilogram degrees Celsius. Okay? So, when I read my problem here, one of the first questions I need to ask, other than what material am I dealing with, is what's my temperature range, and do I have a change of state within that range? And in this case, we do not. So, what I have been given is I have 1 kilogram of water. I know the specific heat of it is 4,186 joules per kilogram degrees Celsius. My initial temperature, which I'll call T naught, is 1 degree Celsius. And my final temperature, which I'll call T, is 99 degrees Celsius. Now, in physics, we typically don't really like to work with Celsius. We like to work with Kelvin, and that has to do with reasons that I had mentioned in the last video. But here, since the difference in temperature in Celsius and in Kelvin are the same, because they both are based off of the boiling and the freezing points of water, then I don't have to convert here. Now, what I'm trying to find is Q. I'm trying to find the heat. Okay? Now, so Q is equal to Cm times delta T. That's 4,186 joules per kilogram degrees Celsius. The mass is 1.0 kilograms. And my change in temperature, I end up, at 99 degrees Celsius. And I start off at 1 degree Celsius. So there's a difference of 98 degrees there. So if I put this into my calculator, let me do that here real quick. 4186 times 1 times 98. I get 410,228 joules. Quite a bit. Now, it's a big change in temperature here. I know it seems like a kilogram is really not that much, but look at the size of the specific heat. Water, it really takes a lot of energy to get water to change its temperature by 1 degree Celsius. So as a consequence, if I want to change this by 98 degrees Celsius, well, it's going to take even more energy to do that, 98 times that amount. So if I keep sig figs, in which I have 1 here, 2 here, 2 here, 4 here, this is just 1 sig fig. So it's going to be 4 times 10 to the 5th joules. So that's how much heat it is. Now, so here's another example. I have 50 grams of lead shot that's at 90 degrees Celsius, and it's been dropped into a container that holds 150 grams of water. Now, the water's initial temperature is 20 degrees Celsius. What I want to know is when I take and I drop this in and I let things come to thermal equilibrium, what is the final temperature going to be? Okay? Now, so thankfully, the lowest possible temperature that I'm dealing with here is 20 degrees Celsius. And the highest possible temperature that I'm dealing with here is 90. So, whatever final temperature that I have is going to sit somewhere in between these two. Now, thankfully, that's interesting, I didn't notice that, degrees Celsius. Sorry about that. In fact, that's going to make my eye cross as I see it. Okay, go away. There you go. Anyway, so, as I was saying, between 90 degrees Celsius and 20 degrees Celsius, both lead and water do not experience any sort of change of state. Now, lead is a solid between these two, and water is a liquid between these two. So if I were to look the specific heats up for these things, what I have is the following. The specific heat of water is 4,186 joules per kilogram degrees Celsius. That's we know that. That was what we dealt with earlier rather. The specific heat of lead, though, is different. If you look up its specific heat, you're looking at somewhere around 128 joules per kilogram degrees Celsius. Now, that's not very much at all if you compare that to water. And a lot of that has to do with the fact that lead is a metal. Now, we know metals have properties like they're shiny if you polish them, they're malleable, they're ductile. But what makes a metal shiny is also what's responsible for metals being really good thermal conductors. So when you take a pot and you put it on a stove and you turn your stove on, the pot itself heats up very quickly. But if you put water in it, it heats up very slowly. Now that's because metals have low specific heats typically, and that has to do with the fact that what's moving the heat around on the inside are the free electrons that are on the inside that make that metal also a good conductor of electricity. Okay? Now, that's the microscopic view though. We're not going to really deal with that right now. We're going to be dealing with that in a chapter or two. So right now though, I just want you to keep in mind that metals typically have these lower specific heats because of the fact that they're very good conductors of thermal energy. Water is not a good conductor of thermal energy. It's what we call a good insulator. Now, we also have some initial temperatures here. We have our lead shot with an initial temperature of 90 degrees Celsius. So the temperature of my lead initially is 90 degrees Celsius. The temperature of my water initially is 20 degrees Celsius. I also know that I have 50 grams of lead, which is the same thing as 0.0500 kilograms. I also have 150 grams of water. It's that many kilograms. Now, that seems to be about all the information that I have. What am I trying to find? Well, when I drop the lead into the water and I let it reach thermal equilibrium, I'm trying to find the final temperature, which I'm just going to call T. Okay? Now here's the deal. In this situation, because the lead has the highest temperature, it's going to lose heat. Now the water has a lower temperature, and its temperature is going to go up, which means its heat is going to increase. So we expect Q to be positive for the water because the change in temperature that it's going to experience is going to be positive. For the lead, we expect it to be negative. The reason is because the change in temperature that the lead experiences is negative. So, whatever energy the lead loses, the water is going to gain. The way we show that is to say that the energy that the water gets is the same as what the lead loses. Now this is going to be negative, this is positive, so we put a minus sign out in front to show, sort of like when we talked about the relationship between work, potential energy, and kinetic energy, there was an intrinsic negative there, that in this case the lead is losing it and the water is gaining it. So C sub W, M sub W, delta T sub W is equal to minus C sub L, M sub L, delta T sub L. Now let me go ahead and plug in the change stuff here. My final temperature is T. My initial temperature is the temperature that the water initially has. On the right hand side, we have this. My final temperature of the lead is T. My initial temperature is the initial temperature of the lead. Now, I'm going to play a little bit of a game or a trick here. This is something that's frequently done to help keep things clean. I'm going to divide both sides by CWMW. When I do that, on the left-hand side, I have T minus TW naught. On the right-hand side, I have a minus sign, and then I have CLML over CWMW times T minus TL naught. Now, I'm going to call this group of stuff right here eta. Now, the reason why I'm doing that is because this is a lot of effort and a lot of possibility, or I won't say possibility, but there is a chance each time I recopy this when I'm solving this equation that I might copy things down wrong. So there's a chance for transcription error. So now what we've done is we've written it the following way. And there's a far less likely chance of me screwing this up when I copy stuff. So what I'm going to do is I'm going to move this to the left-hand side and move this to the right-hand side. When I do that, I have T plus eta T on the left-hand side. And on the right-hand side, if I multiply the negative through, it makes this plus. When this is moved over there, there's positive as well. TW naught plus eta times TL naught. Okay, now I'm going to pull the t's out. I have 1 plus eta here on the left-hand side. On the right-hand side, I have TW naught plus eta TL naught. And then I'm going to divide both sides by 1 plus eta. So T is going to equal to TW naught plus eta times TL naught divided by 1 plus eta. Now, here, if you actually just plug the numbers in for eta to go ahead and do that, let's see here. Let me plug this into my calculator. I have, it's CLML. That's 128 times, let's see, ML is 0.05. And then I'm going to divide that by CWMW. CW is 4,186. MW is 0.15. I get 0.0102. Now it's unitless, okay? And in fact, typically, when we group things up like this, the goal is to make our little constant over here unitless. It just helps make life easy. So if I were to go ahead and plug stuff in, the temperature of my water initially, 20.0 degrees. Eta is 0.0102. The temperature of my lead initially is 90.0. Actually, just 90 degrees. There's no 0.0 there. And then I'm going to divide by 1 plus 0.0102. If I take and I plug this into my calculator here, and what I'm going to do, as usual, is to use the full expression of what that constant is. So that's 20 plus my constant times 90. And then I'm going to divide that by 1 plus my constant. I get 20.71 degrees Celsius. Okay. So I have 1 sig fig here, 3 sig figs here, there's 3 here, there's 4 here, 4 here, 3 here. Really, these are typically taken to be, exact. They're not really, obviously, but just when it comes to how they impact your calculation. Technically, I would round this to 1 sig fig, and when I did, it would just be 20. I'd like to keep this just as a few sig figs to show that really the change that we see here is just in a fraction of a degree Celsius. Now, this may seem absurd because look, you're dumping something that has 90 degrees into something that has 20 degrees, and you're only changing the overall mixture by less than a degree Celsius. I mean, how could that be? Well, the answer to that question is the specific heat of lead. Even though it has a high temperature, it doesn't contain a whole lot of energy. And that's because it only takes 128 joules of energy to raise a kilogram of lead up by a degree Celsius. That's nothing compared to water. So there's very little energy in it per kilogram. Now, likewise, if you take a look at how much lead I'm adding here, I'm only adding, I'm adding about, if you mass by mass, right? It's a third of the mass of water. That's how much lead I'm adding in. So not only am I adding in something that has a very low specific heat, so it doesn't have much energy in it, again, per kilogram, the amount that I'm adding is not a whole lot. Okay, so as a consequence, I don't experience really that much of a change of temperature here. Okay. Now, so let's do another one here. And in this case, what we have is a car. So remember, heat's just energy. So where do you get your energy from? Well, in this particular case, this is going to be the frictional energy due to this car slowing down to rest. Okay, so we have a transformation of energy, if you want to think of it like that. The way that you typically learn conservation of energy, say in grade school, is energy is neither created or destroyed, it's just transformed from one state to another state. And that's exactly what's going on here. You're taking the energy of an object that's moving, and through frictional forces, you're transforming the energy into heat, and as a consequence, that heat is going to go, in this case, into the rotor and the brake pads and the brake assembly, basically, in a car, and cause that to heat up. Okay, so here's what we have. We have a car. It has a mass of 1,250 kilograms, and it has an initial velocity of 30 meters per second. Now, it is going to slow to rest over a distance of 25 meters. So if I think of my car starting here, we'll say moving to the right with an initial velocity of 30.0 meters per second. And it has a mass, m sub c for car, of 1,250 kilograms. As this thing slows down to this point right here where my final velocity is 0, it has covered a distance of delta x equaling 25.0 meters. Okay? So, the energy due to this car slowing down. So there's going to be a frictional force that's due to the wheels as they rotate. So if you don't know anything about how a caliper system works on a car, you have this disc of steel basically that sits attached to basically the back part of your wheel. Okay, it sits between your wheel and the shaft that your wheel attaches to. All right. Now, so there are these things that are called brake calipers, and they have sort of a curved look to them, like this, and they have a plunger that sits on them. And what this plunger does is to push down on a pad. Now the pads are made out of some sort of insulator. In the past, many years ago, they were made out of asbestos. These days, it's a ceramic along with some other stuff and maybe even doped with a little bit of metal in it. Now, what this pad does is it's got a really high coefficient of friction, and it sits there, and when you hit your brakes, this caliper, the piston pushes on the back side of the pad, and it pushes into the rotor. The harder you push on the brakes, the harder it pushes onto the rotor. And as a consequence, what it does is to create frictional drag. So, for example, if the wheel is rotating this way, as this pushes on it, it creates a drag this way. So this would be the direction of, we'll say your frictional force, slowing it down. Okay? So here, the car is moving to the right. The force is acting to slow this thing down. There are 4 rotors in the car, we're going to assume. Most cars have 4 rotors. Older cars have 2 rotors and 2 what are called brake drums that sit in the back. Okay? Now each rotor and caliper, which I'll call IMSA bar, they have a mass of 15.0 kilograms. Now, we're going to assume that their initial temperatures are all 50.0 degrees Celsius. Now, why so high? Well, even as this wheel turns, there's a lot of friction and stuff that's going on the inside. You may not be hitting your brakes, but there's still some drag there, and that keeps these rotors pretty hot. Okay, so your car slows down. It takes work. This is the origin of the work right here to slow your car down. And what happens is that work is going to go directly into heating. Now, so work, we know, causes a change in kinetic energy. Now, my initial kinetic energy is 1/2 the mass of my car times the velocity of my car squared. My final kinetic energy is going to be 0. Okay? So I could use the full force dotted with displacement, since we're going to assume a constant force, or I could do this. I'm going to take this approach because it's way easier. So here, the work is going to cause so it's K minus K naught. So this right here is going to be basically how much work is being done to slow things down. So that said, what are we given? The initial velocity of the car is 30.0 meters per second. The final velocity is 0. The mass of the car is 1,250 kilograms. The displacement, which really doesn't matter here because we're taking this approach to work, is 25 meters. The mass of each rotor is 15.0 kilograms. Like I said, there's 4 of these things, and I'm going to call this M sub F for the braking force, the friction, is 4 times 15 or 60. Okay, so there's 60 kilograms of metal basically that's slowing this thing down. We also have an initial temperature of 50.0 degrees Celsius. Now we're trying to find the final temperature T. Okay, so how much work for part A is done in slowing the car down? Well, the work here is minus 1/2 M sub C V naught squared. Why is it negative? Well, it's slowing down. We're taking energy away from the motion. So, if I take and I plug stuff into this, that is times 1,250 times that square. Okay, so I have 562,500 joules. It's negative because, again, I'm taking energy out. Well, where is the energy going into? Well, it's going into heating. So the amount of heat that's being added is coming from the work. It's being added to it, so it needs to be positive. Okay? Now that is going to act on the steel rotors. Now, I forgot we're dealing with steel rotors. Steel and iron have approximately the same specific heat. If you were to look it up, it would be, let me get my little sheet here, 452 joules per kilogram degrees Celsius. Okay, so C times the mass of the thing that's slowing us down times the change in temperature. Okay, so here's what I have. C m sub f T minus T naught is equal to minus the work, we'll just call it minus W, it's this right here. So if I divide both sides by C m sub f, I get that. I'll move T naught to the right hand side. And now let's plug stuff in. So C was 452 joules per kilogram degrees Celsius. The mass, 60.0 kilograms. And then I have to add my temperature in. That is 50.0 degrees Celsius. And so, let's get my calculator here. Let's see. So, let's divide that by 452 times 60. And then I'm going to add in my 50 there. And I get 70.74 degrees Celsius. 3 sig figs here, 3 here, 3 here, 3 here, 3 here, 3 there. So it looks like my final temperature here is 70.7 degrees Celsius. And how much work was done? Well, again, if I adhere to 3 sig figs, it would be minus 563,000 joules. Okay. Now, 70.7 degrees Celsius is that's pretty hot. Okay, and you can kind of prove to yourself that the act of braking generates heat by starting up your car, say pulling out of your driveway, driving say down to the end of your street, hitting the brakes, turn around, come back and pull into your driveway and hit the brakes. And then when you get out of your car, don't touch the rotor. Don't touch that disc of metal, but try to put your hand near it and see if you can feel the heat radiating it off of it. And you will. You'll feel the heat. Okay? Now, so the next thing I want to do is to talk about what happens when you add heat and you don't get a change in temperature. So that occurs during what's called phase transitions. Now this right here is a phase change diagram for water. We start with ice. This is applied heat. Whoops. So in this situation, what's happening here is you're adding heat. Okay. And this right here is a corresponding change in temperature. Now, 273 Kelvin, this is in Kelvin. This right here for water is when water freezes or when it melts. So at this point right here, you're transitioning from one state of matter into another state of matter. At 373 Kelvin, that's equivalent to 100 degrees Celsius, and that's when water transitions from a liquid to a gas, or if you go the other way, from a gas into a liquid. So in both of these situations, you have a change of state, a change of phase. And what I'd like to point out here is the behavior of the temperature with respect to the applied heat. So if you start off with something like a block of ice that has a temperature that's well below that of its freezing or its melting point, as you increase the temperature, or as you add heat rather, the corresponding change in temperature is linear. Now remember, applied heat, Cm delta T, this is the change in temperature. These are just numbers. This is like a slope. So there's a linear relationship between the amount of heat that you add and the change in temperature that you see. So this is a line, this is what we expect. However, when you get to the point to where you have a combination of ice and water, when your block of ice starts to melt and you get liquid water, what you'll notice is that at that point, when you add heat, the temperature does not change. It stays at 0 degrees Celsius or 273 Kelvin. Okay? Now, once you have converted all of the solid water over into liquid water, as you continue to add your heat, you'll notice that the temperature suddenly starts to go up in linear fashion. Now the slope's different because, if you remember way back over here, the specific heat, which is very closely related to the slope, just through mass, for solid water is different than for liquid water. So, different specific heat, different slope. The same thing goes with steam. Now, when you get to this point right here, 100 degrees Celsius, or 373 Kelvin, what happens is you have a combination of liquid water and gaseous water. As this starts to boil and convert the liquid water into gas, to steam, you'll notice at this point, while it's boiling, that the temperature remains fixed. Once you've converted all of the liquid water into gaseous water, at that point, as long as you're still adding heat, the temperature will continue to go up. So, during a phase transition, it looks like the added heat does not cause any sort of associated change in temperature. What you would discover if you did an experiment is that the only thing it depends upon is how much matter is there. Now, there is a constant of proportionality called L. This is called the latent heat. There are two basic types of latent heats that you see. You have one of fusion, and you have one of vaporization. Okay? Now, the latent heat of fusion deals with how things behave when you're going from a solid to a liquid or from a liquid to a solid. Now, going from a solid to a liquid is called melting. Going from a liquid to a solid is called freezing. And in situations where you deal with melting or freezing, you're dealing with the latent heat of fusion. Why fusion? Fusion means to bind, to connect, to combine. Now, when you go from a liquid to a gas or from a gas to a liquid. That's vaporization. The processes that you have there are condensation. When you condense, you go from a gas into a liquid, or vaporization. Here, you have the latent heat of vaporization. Now, not all materials experience all three states of matter. That's one of the things that makes talking about phase transitions so complicated when it comes to the physics that underlies them. So, it is possible, for example, with carbon dioxide, to go straight from a solid into a gas. Now, you have sublimation, which is the act of going from a solid to a gas, or you have deposition, which is the act of going from a gas to a solid. Now, water actually can experience all three of these. There's something called a trimple point in water, in which you have a combination of all three things going on, solids, liquids, and gases, and it gets pretty complicated. We'll be talking about that later on in greater detail. I'm going to table it because I'd like us to have a little bit better understanding of the physics that's going on. So now, what kind of physics is going on here? Well, if you think of the interior of a solid, again, as being a whole bunch of atoms and molecules that are connected by little springs. Okay, so I'm going to take, again, the lazy approach and just draw a few of these little springs here. I'm not going to draw them all. These have springs too. So when you add in heat, we know what you do is you make the atoms and molecules move faster. But if you think of these as being springs, we know that with real material, there is a limit as to how much you can cause it to move before you tear it apart. So when you're dealing with C is equal to m delta T, this heat right here, or Q is equal to Cm delta T, what happens is you're adding your heat energy in, you're causing the atoms and molecules to vibrate in place more and more and more and more and more. But eventually you get to the point to where your object is so saturated with energy that if you were to add in just a little bit more energy, you start to break the springs. Now in that situation, once those springs start to break, all the energy that you add in goes into breaking bonds, which means that now you're in this regime. Okay? So heat goes into causing the atoms and molecules to move faster. When they become saturated with energy and they can't really take any more without starting to break the bonds that are allowing them to vibrate in place, then you have your phase transition occur. And when your phase transition occurs, all the heat that you're adding in goes into causing that transition. Okay? So, just as an example or two here, how much energy is required to melt 2.0 kilograms of solid lead that is at exactly 327 degrees Celsius? Why 327 degrees Celsius? Well, that's the melting point of lead. Now, the act of melting, or the act of freezing, means that you are dealing with fusion. And the latent heat of fusion for lead is, let's see here, 327,000 joules per kilogram. It takes this much energy to completely convert 1 kilogram of lead at exactly 327 degrees Celsius from a solid into a liquid. Now, how much do we have here? 2.0 kilograms. What are we trying to find? The heat. So here, Q is just equal to L sub F times M, or 2 kilograms times 327,000 joules per kilogram. And when you plug that into your calculator, it's 327,000 times 2, 654,000. Or, keeping to 2 sig figs, 6.5 times 10 to 3, 4, 5, 10 to the 5th joules. Okay? Now let's work another example. S is water. Now the reason why I want to work this is because it covers all the phase transitions that water experiences with the exception of sublimation. Okay? So, minus 15 degrees Celsius, water is a solid. At 0 degrees Celsius, it is a combination of solid and liquid. That's when it starts to experience its phase transition. Then, once it's all transformed, we're heading towards 200. Once it's all transformed, you have to raise your water from 0 degrees Celsius up to 100. 100 is the boiling point of water. You have to boil all your water away, and then take that steam that's left over and raise it up to 200 degrees Celsius. So this is a multiple step process. Okay? So let me just write down my givens, and I'll talk more about the process. So my initial temperature of my water is minus 15 degrees Celsius. My final temperature, which I'm just going to call T, is 200 degrees Celsius. I have a total of 25.0 kilograms of water. I am trying to find Q, how much heat is needed. Now here's the deal. For step 1, what we're doing is we're going from our initial temperature to 0 degrees Celsius. So we're raising it up to the point to where it starts to melt. Step 2, we melt. Step 3, we go from 0 degrees Celsius to 100 degrees Celsius. Step 4, we boil. We vaporize it. Step 5, we go from 100 degrees Celsius to our final temperature T. So, our first heat would be the specific heat of ice times the mass of the water that I have present times whatever change in temperature the ice is going to experience. Part 2, where I melt, is M times the latent heat of fusion of ice. Step 3, I have water now. I take and I raise it from 0 degrees Celsius to 100 degrees Celsius. When I get there, though, now I have to vaporize it. I have to boil it. That is the latent heat of vaporization. The last thing I have to do is to take my steam and change this temperature to 200 degrees Celsius. Now, what this tells me is that I need to know the specific heat of ice, the specific heat of water, and the specific heat of steam. But thankfully, we know that. That was, let's see, here. Here we go. Now, I also am going to need to know some latent heats. I need to know the latent heat of fusion for water and also the latent heat of vaporization. And I'm going to write that over here. The latent heat of fusion for water ends up being 334,000 joules per kilogram. Now, the latent heat of vaporization for water is 2,256,000 joules per kilogram. This is a tremendous amount of energy that goes into breaking these bonds. So, let's just add up our heats to find the total heat. That's going to be the sum of all the heats, of which we have Ci m delta Ti plus mLf plus Cw m delta Tw plus m L sub v plus C sub s m delta T sub s. Now, this right here is C sub I, this right here is C sub water, and this right here is C sub steam. Now, they all have a mass in common, so I'm going to pull the mass out. What I have here left over is C sub I times the change in temperature of the ice plus the latent heat of fusion plus C sub water times the change in temperature of the water plus the latent heat of vaporization plus the specific heat of steam times the change in temperature of the steam. Now let's plug stuff in. How much water do I have? 25 kilograms. Now, C sub I, 2090. What change in temperature does my ice experience? Well, the final temperature is 0 degrees Celsius. The initial temperature is minus 15 degrees Celsius. So that's that. The latent heat of fusion is 334,000 joules per kilogram. The specific heat of water, 4,186 joules per kilogram degrees Celsius. We are changing our temperature to 100 degrees starting at 0. The latent heat of vaporization is 2,256,000 joules per kilogram. So that's taking care of this, this, and this. Now we have our steam. That's about 1,520 joules per kilogram degrees Celsius. Our final temperature is 200 degrees Celsius, and our initial temperature is 100. So, if I plug this into my calculator, that's a pretty long one too. I have, see, 25 kilograms times a bunch of stuff. 2090 times the change is 15 plus 334,000 plus 4,186 times the change in temperature is 100 plus 2,256,000 plus 1,520 times a change in temperature of 100. When I do that, I get a total amount of energy that needs to be added of, excuse me, 79,798,750 joules. Now, 2 sig figs, 1 sig fig, 3 sig figs, 1 sig fig at the end of the day. 3, 6, 7. And that's how much energy it takes. Okay? So, lots of examples, mainly dealing with what you would consider to be empirical relationships between applied heat, changes in temperature, and applied heat and changes in state. Okay? Now, in the next video, I'm going to finish up our discussion about this chapter with a conversation about heat transport. After that, we're going to start to delve into the microscopic realm and see really what's going on when we apply heat. And I'll see you then.